we talk about permutations and combinations with repetition. So now, let us consider a simple example. Suppose that you have some dice, standard dice, cubic, with the numbers from 1 to 6 on the faces. Okay. So if you take into account the order of the number that you get, how many possibilities are there when you throw 3 dice? So this one is, suppose that you have so here I give you the dice in different colors so that they are distinguished. Okay, so suppose that we throw the yellow one first, and then the red one, and then the blue one. So how many different outcomes are there? So for each die, you have 6 different outcomes. Okay? And when you, so our procedure will consist of throwing 3 dice, one after another. So we will use the product rule. And each time we have 6 different possibilities. So by the product rule, we take the product of 6 by 6 by 6, and which gives us 216 outcomes. Okay. So you can generalize. So this particular example, each outcome is called a 3 permutation of 6. A 3 permutation of 6 elements. Okay. So here the elements are the numbers on each die, 1 to 6. So here, in this example, you have n is equal to 6. You have 6 elements, which are the numbers from 1 to 6, and you throw the dice 3 times. Okay. So you get 3. Each time you get the result, and you combine the 3 results, accounting for taking into account the order. Then you have an R permutation, 3 permutations of the numbers from 1 to 6. Okay. So here this this result here is trivial. Okay. It is a direct application of the product rule. You have n elements, and each time you choose an element and you choose R times. Okay. So each time you choose an element and you put it back into the set, and then by the product rule you have n to the power R possibilities. Okay. So now, as an example, sometimes you consider applications of functions from one set to another. So in this setting, we consider only finite sets. Okay. Without loss of generality, for a set of n elements, we can assume that it is a set of integers from 1 to n. And similarly, for a set of n elements, we can take the set of integers from 1 to n. So the question is that if you consider the functions from the first set into the second one, then how many functions are there? So remember that a function is a way to associate each element of the first set to one element in the second set. And if you don't mention anything about the function, then in general we allow each value in the domain to be associated with any value in the destination set. Okay. So here, if we don't have any restriction on the functions, then for any number from 1 to n, you can take any of the n numbers here. So for each element of the domain, you have n choices. So by the product rule, or you can say that it is so this one, each function can be defined as a sequence from f1, f2 to fn. Okay. So you can repeat the procedure. You can choose a value for 1 for F1, and then you choose a value for F2. And without any restriction, the values can be the same, can repeat. So this is exactly so you can identify such a function with an n permutation of n elements. Okay. So here, even though the result is easy, you should do some exercises or look at the definition so that you will not confound between n and n. Okay. So here, the n here is actually the numbers of possibilities for each element. Okay. When you choose m times, so the number of steps is in the exponents. Okay. So now onto the more complicated case. So what about the case if you have two identical dice, or in other words, you can consider throwing the same die twice. Then how many different outcomes are there? So here in this example, we say that the order doesn't matter. That means that if you get first time you get 1, and then the second time you get 2, is considered the same outcome as 2, 1. Okay. So here, since the number of cases is small, you can enumerate, you can list all the possibilities. Okay. So, for example, for easy visualization, you can draw a grid, a table. And one side you have 1, 2, 3, 4, 5, 6, and on the other side you have the same. Okay, so let's say that this will be result of the first try, and here is the result of the second try. Okay, so each time you combine two elements, you have some kind of matrix here. So you have 1, 2, 1, 3, and so on. Okay. So here you can see that if you eliminate the outcomes which are the same, then you get let's try how many you get. So you can see that here you have 1, 4, 1, 5, 1, 6. Okay, so here you have 2, 1, which is the same of. So here, if you notice that then there is some kind of symmetry here. The upper triangle, the lower triangle basically repeat the upper triangle. So you only have to count the elements in the upper triangle. Okay. So you have here. And so on. And below we don't count because they are the repetitions of outcomes which are already listed here. So here, if you remove the repetitions, then you have 6 on the first row, 5 on the second row, and so on. And so the result will be, if you take the sum, you will have 6 plus 5 plus 4 plus 3 plus 2 plus 1, and which gives you 21. Okay? So you can either do the boring way of listing all the possible outcomes, or you can draw a matrix like this, and or you can even apply some. You can use what you have already learned. So suppose that you divide the outcomes into 2 categories. Okay, so in the first one you have 2 different numbers. Okay, if you have 2 different numbers, it's the same as choosing 2 elements from a set of 6. So you have 6 choose 2, and you know how to calculate this. You have 15 possibilities. Okay? And if the two numbers are the same, then of course they can be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. You have 6 possibilities. And you combine the two cases, and you get the same answer, 21 possibilities. Okay? So you can do one of the two ways. So for this example, it is easy. Okay? So now what about the case if we increase the number of possibilities a little bit? Okay? So now instead of 2 dice, you have 3 dice. So the question remains the same, except that we have an additional throw. So how many different outcomes are there? You can try the previous method, and you will see that it will be more difficult. Okay? So now if you try to list all the possibilities, then it becomes complicated very, very fast. Okay, and with 3 dice, it's more difficult to recognize all the repetitions of the case. And instead of a square table, so now if you want to do the same, it's not possible to do the same, because now we have 3 dimensions instead of 2. And you can try. So you can try it at home, but it will be difficult, and it is prone to mistakes because of the number of possibilities. Okay. So is there another more convenient way to deal with this? Okay. So of course there is a very clever way, which is not trivial. So here, what we will the argument that we will use to solve this problem is that instead of throwing a die, we consider throwing a ball into one of the 6 boxes. Okay? Here we have 6 boxes arranged in a row next to each other, like this one, and we give the labels from 1 to 6 to the boxes. Okay? And we will throw a ball into one of the boxes. Okay? So instead of throwing a die, we throw a ball into the boxes, and we have the same possibilities. We have the same 6 possible outcomes, either 1 or 2 or 3 or 4 or 5 or 6. Okay? So it's a different way, but the result is the same. So now, instead of throwing 3 dice, we will throw 3 balls into the boxes, and here is how the result will be represented. Okay? So here in this example, for example, if we get the result 2, 3, and 6, that means that we have 1 ball in the box labeled 2, 1 ball in the box labeled 3, and 1 ball in the box labeled 6. Okay? And here, this example represents an outcome where you have a repetition. Okay? So you have 2 times the number 6 here, which is represented by 2 balls in the box number 6. Okay? So here, this is how we will transform our problem. So instead of 3 dice, now we have balls and boxes, and the question becomes, how many different ways are there to distribute 3 identical balls into 6 different boxes? So here, note that the balls are the same. Okay? So here you have 2 balls in the box number 6, but you don't know which ball is thrown into here first, because the order doesn't matter. So we only care about the number of balls in each box. Okay? So here I emphasize the word identical. So it is important here. Okay? So when the balls are identical, the order is not important. Now that we have transformed, is the problem, does it look easier for you? Or is it the same? Same? Yeah, of course, then there is an additional step which is very clever. So pay attention to how we solve this. Okay, so here, now, this picture will give you the key to solve this problem. Okay? So here we know that. How do we recognize this? So here, these two balls are in two different boxes because there are some kind of separators between them. Okay? So here you can count that this ball is in the box number 2. That means that there are two separators before it, to the left a bit. Okay? So similarly, these two balls are next to each other. That means that there is only one separator between them. And here there are two boxes between the ball, this ball and this one. And the two boxes here correspond to 3 separators. Okay? So now if we remove the bottom of the boxes here, and we suppose that the boxes are arranged next to each other so that between two boxes there is only one separator. Then this picture, this situation 366 can be represented by this one, where we use a vertical line for a separator and of course a dot for a ball. So here, if you remove the numbers and the bottom of the boxes, then from this picture you can still recover our configuration. Okay, so here, what is the outcome corresponding to this picture? So you count, okay? So here since the two outermost separators are not important because you cannot put the ball farther to the left or to the right. You can remove the two outer separators as well. So in total you have 1, 2, 3, 4, 5 separators between the boxes, okay? And 3 balls. So here this configuration is, so here this space here corresponds to the box number 1. This space here between the first 2 separators corresponds to the box number 2. So this is the box number 3. So you know that there is a ball here. It will become so this is 3, and here is 4, 5, and 6, 6. Okay? Whenever we have another separator, we increase the number of the box by 1. Okay? And so now you have a unique representation of each outcome by an arrangement of the separators and the balls. Okay? In a row. Now you have a row, something in a row. And now we will denote each space occupied by a separator or a ball by a space here. So here we add the spaces, and you will have how many? You have 5 separators and 3 balls. So you have 8 places for separators and balls. So now, whenever you try to arrange 5 separators and 3 balls into a row, you will have an outcome of the 3 throws of the dice. For example, Okay, so now let us do it in a slower way. So now you have 8 places here. Okay, so suppose that you have balls in the first 2 places, followed by a separator, and then balls, then a ball, and then the rest are separators. So what is the outcome corresponding to this configuration? So here it is before the first separator, so you know that this is the box number 1, okay? So here is the box number 2, and then you have 3, 4, 5, and 6. So this corresponds to the configuration where you have 1, 1, and 2. Okay? And similarly, if you put a separator here instead, and then a ball here, then we will have another situation where so here 1 now become this part, and you have 2 and 3, 4, 5, and 6. So this will become 3, 2, 3, and 4. Okay? So now, so the key word here is unique. Okay? Unique means that for each arrangement of 5 separators and 3 balls in a row, you have one and only one outcome. Okay? So since there is a 1-to-1 correspondence, we conclude that the number of outcomes will be equal to the number of ways to arrange the 5 separators and the 3 balls in a row. Okay? And now that you have this configuration, you have already learned the way to solve it. Okay? So you have 8 places. You will choose 3 out of 8 for the balls, and the rest for the separators. So the answer will be 8, choose 3. Okay? Or in other words, if you prefer to choose the places for the separators first, then you have 8, choose 5. And of course, the 2 give you the same results. Okay? So you can either use 8, choose 3 or 8, choose 5, and the answer is 56. Okay? So here you can remark that in the first example where we allowed repetitions, we had 216 possible outcomes. But now that we ignore the ordering of the result, then we have a much smaller number. And so here you can generalize this result to get this general formula. Okay? And so now I will tell you in terms of boxes and balls. So here, if you want to put R balls into N boxes, R identical balls into N different N labels or N numbered boxes, then the number of ways is this one. Okay? So here, each outcome is called an R combination of N elements. Okay? So here, in this language, R is the number of balls and N is the number of boxes. Okay? The boxes or the labels are the elements, and the balls are the tries, the number of objects put in the boxes. Okay. So now, of course, the proof is basically the same as the illustration that we used for the previous example. Okay. So here we put our n elements are the n boxes, and the number r here is equivalent to r balls. Okay. So for n boxes, we have n-1 separators. We only count the separators between the boxes, and we ignore the outermost separators. Okay? So now we have n-1 separators and r balls arranged into a row. Okay? So the number of ways is exactly the number of ways to choose r places for the ball out of n plus r-1 places the whole. Okay? Okay, so what is important for you is to understand in this language what is the between r and n, which is the number, which is the ball, and which is the boxes. Okay, so when you do in the exam, you can bring your notes, so you can write down the formulas. Okay. But in order to be able to use the formula, you have to understand what each symbol in the formula means. So here, the important thing to remember is that r is the number of balls and n is the number of boxes. Okay, and for n boxes, there are n-1 separators. Okay, so you don't forget the -1 here. Okay. Okay, so now let us consider some example where you can apply that formula. You can see that without the previous formula, the problems like this one will appear difficult. But now that we know the formula, you can apply directly the formula to find the result. But of course here, the important thing is that you determine in this kind of setting which are the balls and which are the boxes. Okay? So here you have 4 different kinds of cookies, and you want to buy 6 of them. Then how many set of 6 cookies can you choose? If you have 4 different kinds and you assume that cookies of the same kinds are the same. Okay, so here, what are the balls? The cookies are the cookies balls or boxes? Now you have you have 4 different kinds. Okay, so here you have 2 numbers. You have 6 here and 4 here. So which one is N, which one is R? So in other words, what can be repeated? What can be repeated? The type of cookies can be repeated. Okay? So that means that what in our previous setting, what can be repeated are the boxes. Okay? So here the type, the kind of cookie can be repeated. So N is 4 and R is 6. You suppose that you throw some token into, you have 4 boxes of cookie and you throw a token into the boxes, and each time if the token fall into one box, you will take out a cookie from that box. Okay? So here you have 4 boxes and let's say 6 balls. So n is 4 and r is 6. So the total number of places is 4 plus 6 minus 1, which is 9. Okay? And you can use either 9 choose 6 or 9 choose 4 minus 1, which are the same, and which gives you 84 ways to choose 6 cookies from 4 types. Okay? So now here is another one, which at first sight is not related to our problem, but indeed it is an application of what we have seen in our formula. So how? Now the question is that you have an equation like this one. You have 3 variables, integer, non-negative integer variables. x1 is 2 and x3. That sum up to 11. And the question is that how many such triples of integers are there? So for example, you have 0, 0, 11. Okay? Or you can have so here at first sight you can see that maybe there are no repetition because these are 2 different solutions. Okay? So how can you transform this into our setting? So what are the boxes and what are the balls? Can you guess? Do you have an idea? Now suppose you have, but if you look at this, if you compare this, if you think of the previous example, you can imagine that you have 3 types of cookies. Okay? You have 3 types of cookies and you want to take 11 of them. And how many ways are there? So what is n and what is r? So here each variable corresponds to a type of cookie. Okay? You have the first type of cookie, the second type, and the third type, and you want to choose 11 cookies. So here, as we said, the types of cookies correspond to n. So here you have n is 3 and r is 11. Okay? So now once you have determined n and r, it remains to apply the formula. And you get this. Okay? And of course in the exercises you can generalize this to equations in which the variables are integer but maybe not negative or maybe bounded and so on. Okay? For example, if I modify a little bit, now I want to count the number of solutions which are not only non-negative but strictly positive. Then how you can try how many solutions are there. If I change a little bit which word, if instead of non-negative I put strictly positive, then how many solutions are there? You can try. And of course you can do those exercises in tutorial classes. And I think that after some exercises you will get used to them. Okay. Okay, so now the bottom line is that for these exercises, for this kind of application, it is important to determine which one is R and which one is M. You can always think of the example of the cookies or the example of balls and boxes. Okay? And you will practice more in tutorial classes. Now, so in the previous examples, we didn't have restriction on the number of repetition. That means that you can have any number of cookies, okay? Of course, bounded above by the total number of cookies. But now, we consider this different setting in which the number of repetitions are fixed. So for example, you have a word here, or a string, success, and you will you want to shuffle the letters of this word. Then how many different strings can you get? Okay, so now we cannot apply the previous formulas because here each shuffle word must have exactly how many S's? Exactly 3 S's, 1 U, 2 C's, and 1 E. Okay. So how many different strings can you obtain? But this one is actually much easier than the previous one. Because here you can apply the rules and the formulas about combinations and permutations that you already know. Okay? So now, do you have an idea how to count? How to answer this question? So here, since you know exactly the number of places, so here first we count the number of letters. So we have 7 places. Okay. So here you can rephrase the question is that you have seven empty places. You want to put in those 7 places 3 S's, 2 C's, 1 U and 1 E. How many ways are there? You know, right? You can derive a sequential procedure to get the result. Okay, first you have 7 places. You have okay. You first you choose the places for the 3 S's. Okay, since the S's are the same. The order doesn't matter, so we only have to count the number of ways to choose 3 places, and then you put the letters S into those 3 places. Okay, so first you choose in the first step you have 7 choose 3 ways. Okay, so once you have fixed the 3 places for the letters S, there are 4 remaining places, and out of 4 remaining places, you have to choose 2 places for the letters C. So you have 4 choose 2. Okay. So after this, you have how many places are left? You have 4 minus 2. That is 2 remaining places. Okay. So out of the 2 remaining places, you have 1 U and 1 E. So you have 2 ways, okay? Either EU or UE. So in the end, so since you do all these steps one after another, you apply the product rule. Okay? And you get for 20 different outcomes. Okay? So, in this method, you can first consider all the permutations of the letters. You suppose that first you ignore the repetitions. If you ignore the repetitions, you have 7 factorial permutations. Okay? But now some of the permutations are repeated because there are some letters. And how many repetitions are there? You know that if you shuffle the letters S, then you get the same string. So for each string, you have, in fact, 3 factorial repetitions caused by shuffling the letters S. There are 3 S's, so there are 6 repetitions by S. And if in addition you shuffle the 2 letters C, then you have 2 factorial, and here you multiply the 2 factors together. So you have a factor of 6 caused of the 3 S's, and you have a factor of 2 caused by the 2 C's. And of course, if you want to count, you have 1 factorial caused by shuffling the letter U, since there is only 1. It stays at the same place, so you can ignore the letters without repetition. So if you apply the division rule here, you get the same result, 420 different strings. Of course, once again, you have the same number. Okay? You can count in many different ways, but you always have to get the same result. Okay, so in general, you have this formula. So there is no. In fact, this formula is generalized of the method 2 that we have used in the previous example. Okay, so suppose that you have a set of n objects of n1 objects of type 1, n2 objects of type 2. And in each type, the objects are the same. Okay? So if you repeat the procedure that we have used, then if you choose the places for the first type, then you have n choose n1. Okay? And next, after we have fixed the n1 places for the first type, we have n minus n1 places left, and then we will choose n2 out of these places, and so on. And then you have n minus n1 minus n2, choose n3. Okay? And you repeat the procedure. And here, note that n here denotes the sum of n1 to nk. So in the end, you have only n1 places left to choose. Okay? So now you have this formula. So it should look like this. But you can develop this formula and simplify in order to get the result. Okay? So you know that here you have n factorial divided by n1 factorial times n minus n1 factorial. Okay? And the second factor you write as n minus n1 factorial divided by n2 factorial times n minus n1 minus n2 factorial, and so on. So you can notice that the numerator of the next factor, the next term, okay, is cancelled out by is present in the denominator denominator of the previous factor. So you can simplify this one. And similarly, this term is present here, so you can simplify. And in the end, only these remain. Okay? So if you write this product here, so of course on the slide I give you a simplified version, and you have to, if you want to convince yourself of the formula, the correctness of the formula, then you have to develop this and simplify in order to get the final result. Okay. So here this formula is actually in the okay, so here you have the final result here. The final formula here, and here in the method 2, actually you have this formula. In fact, the two formulas are equivalent here. And for convenience, once you already have this formula, you can use, or maybe it is more computationally convenient to use this formula, because these factors here are smaller. So you can, if I have to program, or if I have to calculate some specific result, then I would use this form here. Because if you use this form, then you have to calculate n factorial, which is a huge number, so it is not efficient to use this one. I'd rather use this one. Okay, so it's up to you. You can use either one. Okay, you will see. Okay, so I suggest we take a short break, 5 minutes, and after that we proceed to this next part. so in the next part we will consider a more general setting where we try to count the number of ways to arrange some balls into some boxes. Okay. So here we haven't specified whether the balls are different or the same, and whether the boxes are different or the same. But in fact, that so we will consider four different cases. Okay. So depending on whether the balls are identical or different, or whether the boxes are identical or different, we will have four different cases. Okay? So the first case is when the balls are different from each other and the boxes are different from each other. Các bạn ở sau vào thôi được không? Okay, so in fact, some of these cases are repetitions of what we have already seen in the first case. Okay, so you see that when the balls are different, or here, we use the term distinguishable, and the boxes are distinguishable. It is as if we count the number of ways to put n distinguishable balls into k distinguishable boxes. Okay, so here I cheat a little here. So in fact we fix the number of balls in each box. So here we cheat a little by fixing the number of balls we allow in each box. So we have n distinguishable balls. So in general we have n permutation ways to arrange them, and I'm sorry, this setting is not clear enough. In fact, the balls are in different types, but inside each type they are the same. So it's the same setting as the problem permutation with repetition that we have seen in the first part. So here is not exactly this description, but we repeat these results. So if we put n balls into k boxes, so that the number of balls in each box are fixed, and we don't take into account the order of the balls inside each box, then we have this many ways to do it. Okay. So now, as an example, consider a tournament where there are 32 teams. They are divided. They participate in the group phase, in which the teams are divided into groups of 4. And since there are 32 teams, we have 8 groups. And suppose that we choose the groups randomly. There is no restriction, no seeding, and no such thing as teams which avoid each other. Suppose that the draw are completely random. Then how many results are there? Suppose that the groups are labeled from A to H in advance. Okay, here so it is easy, right? First you choose 4 teams for group A, then you choose 4 out of the remaining teams for group B, and so on. And then you multiply the results with each other. Or you can also apply directly the formula, and you get this huge number. Okay? So I don't know, this is roughly 3 billion. Okay? So it's a huge number if there are no restriction. So even if you take into account the permutations of the group, you divide this result by 8 factorial, is still a big number. Okay, so to this case where we have the balls are the same, but the boxes are different. So this is exactly the case that we have seen with the cookies and the types of cookies. Okay, so we repeat the formula here, just for the sake of completeness. So we put R identical balls into n different boxes, and the result is this. Okay, so if you count the separators between the boxes, we have R balls and n-1 separators, and the balls are the same, the separators are the same. The result will be the number of ways to choose R places for the balls out of R plus n-1 places in total. And you have this number. Okay? So now, this is the third case is a new case where the balls are the same and the boxes are the same. So only the numbers of balls in the boxes matter. Okay, so let us illustrate with an example. So now you want to. Okay, so now you want to organize your office. You have 4 different employees. Okay, and you have three offices which are the same. Then how many ways? How many ways are there to organize the seats of the employees in the offices? Okay. So now you suppose that each office is large enough to accommodate as many as 4 employees. Okay. So now, as with the previous example, before we derive some formulas, we have to look at the small cases and we try to guess. So now, let us investigate this example. So you have 3 offices, you have 4 different employees. Okay. So let's say that our employees are named A, B, C, and D. Okay. So first, before we put the employees in the offices, we have to determine how many employees we will put in each office. Okay. So the first case is the obvious one. We can put everyone in the same office, since the offices are the same, this case is basically the same as 040 or 004. Okay? So we have this case where everyone get into the same office. So the second one is 310. Okay? So in this case, in this setting, 3 of the 4 employees will be in the same office and the other one will be isolated in another office. Okay? So as with the previous case, this is the same. Okay? So 310 or 031 are counted the same as this case. Okay? Okay, so there is no other case where there are 3 people in the same office. So the case where there are at max 2 people in the same office, we have 220 or 211. Okay? So if we consider the number of people in the offices, then we have 4 cases like this. Okay? And now we will get into the detail. We will see with 4 people A, B, C, and D. For each big case, like this one, how many detailed cases are there? Okay, so for the first case, we have only one possibility. We put A, B, C, and D in the same office, and the other offices are empty. Okay, so here in the first case, we have one way. So in the second case, where you have 3 people in the same office and 1 isolated one, how many ways are there? How many subcases are there? So in this scenario, the isolated employee can be either A or B or C or D. So you have either ABC in one office and D and empty, or ABD, C and empty, and so on. So the isolated one can be ABC, D, or ABC or D. So you have 4 cases here. Okay? Now, the third case is a little bit tricky. Okay? So for this one, you have 2 and 2. So I will let you count yourself. This case 2 and 2. How many subcases are there? Do you know how to? You can list all the possibilities, or you can use a formula. Okay. So if the number of people in the offices are 220, and how many cases are there? How many ways are there to organize 4 employees in those offices? Anyone has an answer? So, what do you do? 2 people for the first office, and then can you give me a number? How many? So you have A, B, C, and D. Okay, and you want to put them into, you have 2 places in the first office, 2 places in the second office, and here you, in the third office, you leave empty. And how many ways are there? How many? 6? Okay. In fact, the answer is not 6 because why? Because if you count in the normal way, then you have, for example, A, B, C, D here. Okay. But here, it is here that the fact that the offices are the same will be taken into account. So if you count 6, that means that you have distinguished these 2 cases. Okay? If you only count the number of ways to choose 2 people for the first one, then you put the 2 other in the second one, then you have 6 cases. But there will be repetitions because basically AB and CD are the same as CD and AB. So in fact, if we list all the possibilities, then we have only three ways, but not 6. So because you can, in here, the 2 offices are indistinguishable, you can swap them. So you have to divide 6 by 2 because by swapping the 2 offices, you double the number of possibilities. Okay. So in fact, it is not 6, but 6 divided by 2. And in the same way, for the final case, you have not. So here, if you count in a normal way, then here you have 4 choose 2, and then you have 2 choose 1, and then 1 choose 1. That will give you 12. But here, the second and the third office, these 2 offices are the same. So by swapping these 2 offices, in fact you have double the number of true possibilities. So you have to. So here you have repetition here. So you have to take 12 and divide it by 2 factorial. So you get 6. So the final answer is 14. And it seems that there are no formal way, but in fact there is a formula for this problem. Okay? So we will define. So this is an example. Okay, so if we use the language of balls and boxes, then here we have identical boxes. So here we have identical offices. So here the offices play the role of the boxes, and the employees, since they are different, they play the role of the balls. Okay? So here, if we generalize, we count the number of ways to put n different balls into k identical boxes, so here this is important. So this condition is not present in the previous example, but we will see. First we need this condition for this definition, and then we can generalize. We will use this for the more general case where we allow empty boxes. Okay. So now first, if we impose the restriction that the boxes are not empty, and we have n balls and different balls and k identical boxes, then the number of possibilities is called the Stirling numbers of the second kind. Okay? So Stirling is, I think, is a Scottish mathematician, and you have a famous approximation in calculus, the Stirling asymptotic formula. Okay, so it's the same mathematician, and there are several numbers named after him. So this particular number is called the Stirling numbers. But since there are different Stirling numbers, this one we specified the Stirling numbers of the second kind. Okay, so we denote the Stirling numbers of the second kind by S and K. So here, remember that here the order of the parameters is important. Okay, so the first parameter is the number of balls which are different, and the second number is the number of boxes. Okay. So you can, you can remark immediately that if the number of balls is smaller than the number of boxes, then the number of ways is 0 because of this condition. If we want that every box is not empty, then in each box there must be at least one ball. That means that if we want to arrange, to have some way to arrange the balls into the boxes, then we must have at least as many balls as boxes. That means that n must be larger than or equal to k. So if n is smaller than k, then this number s and k is 0 automatically. Okay. Okay, so you can try to find with some small values of n and k to find s, n, and k. And of course, the formula is not trivial. The formula is a sum with the terms are alternately positive then negative. Okay, so here you can see whenever there is a -1 power something, you can see that if I is 0, then the sign is plus. So in general, if I is if the index is even, then the sign is plus. And if the index is odd, then the sign is minus. So this is an alternate sum of this term. This formula can be proven, but we will need more advanced knowledge. So we will see at the end of the first part of counting, we will be able to prove this formula. But for now, we will admit this formula. And of course, for formulas like this, it's good if you memorize by heart, but if you don't, that is also okay because you have access to documents and notes during exams. So, of course, so here this is the formula for the general Stirling number of the second kind. Of course, in this I don't write on the slide, but you must note you must pay attention that this formula applied in the case where n is greater than or equal to k. Okay, so if n is smaller than k, this number is 0. And so, of course, once we have this formula, we can generalize for the case where there may be empty boxes. Okay? So if the boxes may be empty, but we know that there are k boxes, then the number of non-empty boxes can be any number from 1 to k. Okay? So in that case, if we want to count the number of ways to put n different balls into k identical boxes, and we allow empty boxes, then so I will write here, we take the sum of Stirling numbers for k going from, for j going from 1 to k. Why? I will explain it here. Okay, so if you have n balls, okay, and k boxes. So if you have only one non-empty boxes, then the number of ways is as n1. And if you apply this formula, then you can see that if k is equal to 1, then this sum consists of only one term. Okay? So you can write it here, which is 1 over 1 factorial and minus 1 to the power 0, 1 choose 0, and 1 minus 0 to the power n. And of course, this is 1. That makes sense, right? If you have only one box and you put everything into that box, there is only one way. And if you have two non-empty boxes, then the number of ways will be as n2, and so on. And you repeat, and since you have k boxes, you have k cases, okay, as nk. Then, since the cases are disjoint from each other, these are different cases, we apply the sum rule and we take the sum. Now, let us return to our example. So now I would like you to apply the formula that you have seen to this problem. Okay? So now the question is, you have 4 different people and 3 identical offices, and you want to count the number of ways to organize these 4 people into the offices in which we allow empty offices. Okay? So here I leave the formula here, and it is your. Now, do some exercise and try to see if you can get the same result as we previously found. Okay, so you have calculated the numbers. So what do we use here? Which of these formulas can be applied to our problem? We have four people and 3 offices. Then what is N? What is K? First thing, before you do the calculation, when you want to apply a formula, you need to see what will be the value of each parameter in the formula. So, which formula do you apply? What is the case here? Here we have 2 cases. We have a case where the boxes are not empty, and we have a more general setting where some of the boxes may be empty. Which one do we use? Okay, so the second one, since we allow the offices to be empty, so what is N and K here? Okay, so we decide to apply this more general formula. So what is N and what is K? Is N the number of people or the number of offices? So here we have the balls, N balls are different. The boxes are the same. Only the number of balls in each box counts. So here the people are different, so the people correspond to the balls in the terms of this definition, and the office are equivalents of the boxes. Okay? So what is N and what is K? So N here is how many people are there? 4. K is 3. So what do we need to calculate? According to the formula below here, we need to calculate S for 1 plus S for 2 plus S for 3. Okay? So this term corresponds to the case where there is only one non-empty office. We put everyone in one office. And this term corresponds to the case where there are 2 non-empty offices. And this term corresponds to the case where all the offices are non-empty. Okay. So now, if you haven't found yet, I will leave you another 5 minutes to apply this formula to calculate, to give me the value of the 3 terms here. And I think that if you want to apply this formula, you need a pencil or a pen and a piece of paper. Okay, so what is S41? That is an easy one. 1, okay? So S42. Okay, so S42 is 7. So glad that someone actually did the calculation. And S43, 6. So if we take the sum, you get 14. Same number as the one that we found. Okay. So if we go back to the previous slide, then you see that here this corresponds to S41, where there is one non-empty office. Okay. So the two middle cases correspond to the case where there are two non-empty offices. You have 4 plus 3, which makes 7. Okay. And lastly, the fourth case corresponds to 3 non-empty offices, and then you have 6. So, either way, we have 14 ways. Okay, so there are many identities corresponding to the Stirling numbers of the second kind, and this is one that you can easily prove. Okay, so you have this identity relating a Stirling number of the second kind with n plus 1 and 2 Stirling numbers of the second kind for n. Okay? So the idea is that as with other identities, you can always prove this by algebraic method. You can apply directly this formula and do some labor work to arrive at this conclusion. But if we want to do it in a lazy, more clever way, then we can try to interpret what does these symbol or formula or whatever means. So you know that this Sn plus 1k is the number of ways to put n plus 1 balls into k non-empty boxes. Okay? And if we look at this, then Snk is the number of ways to put n balls in k non-empty boxes. And this one is the number of ways to put n balls in k minus 1 non-empty boxes. So we want to make a connection between a way to put the n plus 1 balls into k non-empty boxes to one of the two cases here. Okay. So here you can see it on the slide. So the idea is to count the number of ways to put. So you know that is the definition of the left-hand side. But we want to count the number of ways to put n plus 1 balls into k non-empty boxes in two different, in another way. We want to distinguish two cases, okay? So that one case gives us the first term in the sum here, and the other case gives us the second term, okay? So that is a double counting argument. So how can we arrive at the first term? Do you have any idea? Now here we pay attention to the fact that the balls are different, are distinguishable. Okay. So there are some conditions some important condition. First, the boxes must be non-empty, so that we need to put balls into the boxes. And secondly, the balls are different. So how can we? So here we have on the left hand side we have k non-empty boxes, and on the right hand side we have, in the first term, k non-empty boxes, but in the second term we have only k minus 1 non-empty boxes. So what makes the difference? So if we single out the last ball, so let's say that we look at the ball number n minus 1. So the plus here, remember when we apply the sum rule, that means that we have two different cases. Okay? So if you remember when we have something similar to the Pascal identity, we count the number of subsets or something. We had an example in which we single out an element and we consider the case where that element belongs to a subset of its own, or it shares a subset with some other elements. So here we consider the same way with the ball number n minus 1. So case 1, the ball number minus 1 is in its own box. Okay? The first case is that this ball is in a box, and in that box there are no other balls. Okay? So the number of ways corresponding to this case, in fact, is the same as the number of ways to distribute the other balls into the remaining boxes. So we have n other balls and k minus 1 other boxes. Okay? So this case will give you the second term. Okay? So one way to put n plus 1 balls into k boxes so that the ball n plus 1 is in a box containing only that ball is in fact equal to the second term. So S and k minus 1 way. Okay? So case number 2. Of course, if this ball is not in a standalone box, then that means that it is in share a box with some other balls. Okay? So what does it mean? So in the first case, I repeat, first we choose a box for the ball n plus 1. The procedure is that first we choose a box for that ball, and then we put the other balls into the other boxes. Okay? And we have 1 times this many as nk minus 1 ways. Okay? In order to count the number of ways corresponding to the second case, we will first have k boxes, and since the ball number n plus 1 shares the box with some other balls, if we take out that ball, then we have k non-empty boxes. Okay. So that means that first we can distribute the other balls into k boxes so that none of the boxes is empty, and then we choose one of the k boxes and we put the last ball into it. So that's why you have a factor k here. So first you distribute the n balls into k boxes, you get s and k ways. Okay. And then after that, you pick one box to put the last ball into. So there are k choices for the box that contains the ball n plus 1. So that's why you get this term here. And by the sum rule, we take the sum of the result of the two cases and we get this formula. Okay? In fact, this one I can, there is no formula, this is just a general concept, so we will continue next time. Okay? So as usual, the slides and the exercise list are on Moodle.